People want to keep going, right? Learn today? You want to have a debugging day? Or you want to learn today? Because we can build Slack in, you know? There's an obvious Slack day right here. We could move this around. I can find out when Lucia arrives. Or we can talk about relaxation value. Once you start doing boundary value problems and initial value problems, you're going to have all of the tools necessary in order to actually code your project, right? So right now you probably have 75 to 80% of the tools that you need. And by the time that you get through chapter 9, you're done, right? And so you can really think about it, start working on it in earnest. Now, of course, there's other, right? Keep going and you learn more. And so you make your project, you fine tune it, you learn a little bit more in detail. But there's some flexibility here with everyone being at APS. I would like to put you in a really good position. Oh, we're good.
Going?
Yeah, sorry. Oh my God. Who just came in here? James just came in here.
Oh, got it. Okay.
Yeah.
For you.
Yeah.
Okay, doing the same thing as last time, though.
Yeah, and I just pulled the blue one out.
Cool.
Pulled it out, put it back in. It worked. Yeah.
Perfect. Awesome. Thank you.
Thank you. Okay, so what are folks feeling? You have a preference? So last Wednesday we did 8.6 boundary values. And what this was doing was introducing to you something called the shooting method, which is where instead of knowing, perhaps we have these problems where we start at one location and we just follow it to wherever it goes, right? The shooting method, the boundary value problem, you say that you know where it starts and you know where it ends, but you don't know the path to get there. And so you simulate a variety of paths until you find the one that gets from point A to point B, right? This is important because it's going to lead us into 9.1, which is, let's say that you're simulating something on a two-dimensional array, right? And think about either your computer screen, the boundaries at the very end, they might be fixed. So they might be periodic, they might be held to a specific value. And the solution has to be found within that box, right? Because all simulations have to be done pretty much in boxes because they're on a computer. So these two are going to sort of fit into each other. We can certainly just jump into this and we can see those relationships.
The day that has a question mark, that would be like, a debugging day, we have like questions about homework and stuff to get caught up.
It could be, yeah. It really depends on where we end up in the next 2 weeks. What?
Right, first of all.
It's right before spring break, yeah. So that could be a day that we talk about how you're going to do your code, how you're going to start to think a bit on the break, etc. Okay. Raise your hand if you want 9.1. You can raise your hand multiple times. Raise your hand if you want coding and debugging. Raise your hand if you want neither. All right, good. All right, let's do 9.1. Yeah, so see here, the double pendulum. That's already a problem. So it should be about 1.5 homeworks. And remember, homework is about 3 problems. So think about, if you want to do something like this, we can make it more challenging. You could have maybe 3 pendulums or n pendulums, right? N pendulums is the simulation of a rope. Which is pretty cool. What? Never thought about that before, right? Well, at least that's how, a lot of things will simulate them. So if, for example, you wanted to get into video games, right? What are the best video games Like, what is the thing that makes them unique and beautiful? Graphics, and the graphics is run by computers. Yes, of course they're run by computers, but it's run by physics engines. So every year, right, you have something like, oh, the new GTA just come out and it looks so realistic, right? Well, what do we mean by realistic? It means that when you drop a rope, it behaves like ropes do when they're dropped. When someone's hair moves, right, it looks like hair is actually moving. And importantly, there's something called radiative transfer, which is the process of how light scatters through things like haze and air. And that is really hard to capture, but it's all physics. So if you thought to yourself, man, I don't really think I want to go into academia, but you want to go into designing video games, that's an entire career, right? Okay. And it starts with this. We're going to talk about partial differential equations today. Unless someone else wants to present. No? Anyone not presented yet that wants to? Okay. All right. So what we're talking about here is we're moving away from the realm of objects that only depend on one variable, right? So a partial differential equation, what does this part mean?
Two things that are equal.
Yeah, inequality. I'm gonna need one of these, right? An equation. Differential,
What sort of derivative?
yeah, some form of a derivative. Okay. Oh, what's a partial? Partial derivative.
Focusing on one variable.
One variable, right? So this one here, you see the little curly, that curl, that represents that it's not a normal derivative, but the partial derivative. It's a derivative with respect to x of a function that may include x, y, z, etc. Okay. So the easiest way to start this type of work is to look at electrostatics. Has anyone here taken E&M? Currently taking E&M? What's that? Finish taking it? Yes? No? Yes? Okay. So what are electrostatics?
Problem where charges are not moving.
Charge is not moving, right? Good. We're not worrying about the magnetic fields here. Nothing's moving. We have a collection of charge, and we're going to figure out what it looks like. Okay. So the first part here is del dot E equals 0. What is that?
Means like when we take the partial derivative, we got it with the electric field, it's equal to 0.
Okay, you're reading the math, which is fine, but what does it mean in English? It's not the curl, right? Because it's the del dot. We want to think about the physical interpretation of this statement.
There is knowledge.
What? It's not that there is no electric field, right? It's del dot E equals 0. Okay, so you see the divergence. Del dot means divergence, right? And this del dot E means the divergence of the electric field. That doesn't really have any meaning to me if I don't know what it is, right? So essentially what this statement is saying here is that, think about what the word divergence means. Going away from or coming towards. So yeah, go ahead. Oh, no, that was your hands. Okay. Yeah, so going away from or coming towards. So think about lines emanating from something, right? And essentially what this says is del dot E, for stuff to move away from the electric field, to move away in electric field space, it needs a reason. And it's 0 in the absence of any electric charges. So what this says is I can only generate electric field from charges. Does that make sense? Now, typically, this del dot E does not equal 0. Typically, it equals rho enclosed, which is the density of charges enclosed in some space. That will be del dot E, the reasons for your electric charge or electric current, electric field. Does that make sense? Do we feel that like interpretation? Or is that still kind of opaque?
I don't understand how that's different than saying there is no. Because you're saying the absence of electric charges?
Because you're thinking E is 0. I'm saying we can construct that the E changes in such a way that the derivative of E with respect to X plus the derivative of E with respect to Y plus the derivative of E with respect to Z all cancel. Right? So what we're going to do here is we're going to say, okay, we have another statement here that E is a vector, or E is given by the vector potential, the gradient of something called phi. Right? And if I put these in here, I get del dot del phi, which is del squared phi. Okay? And for the first part of this class, we're going to treat this as solving something called the Laplacian. Right? Laplace's equation says we're going to take a double partial of this thing. So it's written like this. And then we're going to have it equal 0. Later, we're going to introduce charges. So the right-hand side is not going to be 0 anymore. Does that make sense? Yeah.
And it's really faint, but next to that gradient of E, there's a negative sign, right?
What? Oh, here?
Yeah.
Yeah. Well, we don't care about the negative sign when it equals 0, right? What? Yeah, when it equals something, then we have to care about it, right? When we get to this section that looks at charge, it will be important, right? So let's do it. Okay. Here's the box. It's empty. No charges inside. That also means no air, right? Actually empty in this imaginary world. And it's really convenient because we know how to make a box in computational. How do you do that? How do you make a box? What is a box on a computer? Good. Yeah, that would be all 3 dimensions. You're thinking about the volume. Is there anything that we can think of that represents a box to a computer? An array, right? And that can have length times width. It can also have height. It could also have more dimensions, n-dimensional box, because we could have n dimensions in our array, right? So we know how to make this box. So we can say how large it is, how tall it is, right? And then we can fill the inside with 0. And now just the edges have meaning, right? So this says all the walls are grounded at 0, except for the top, which is some voltage, right? So this is 0, 0, 0, and then the top is V. And it's going to ask you to find out what the E field looks like inside. Is that possible? Yeah, because all we have to do is we have to take the Laplacian, which is okay, because there's no electric charges inside the box. And we're basically going to fit the boundary conditions and let them tell us what the inside of the box should look like. So we'll take this box and we'll solve this, right? And we'll successively solve it over and over and over until it gives us 0. This is something that we call the shooting method or the relaxation method. Okay, we're gonna let the solution move towards the one that actually fits the equation. Okay. So let's try that. Nope, that's not what I want. Okay. So let's do it in 2D. Here is del squared phi del x squared and del squared phi del y squared. So we can break this del squared into this derivative. Do you recall this from chapter 5? Now, you're going to read this and you're going to read it wrong. Okay? This looks like phi x plus a minus y. Is phi a function that you're going to call in your code? Phi is going to be your array. So these are the locations. This is I and j. Right? Now what this is saying when we say x plus a, that is just where you're starting plus 1. Some distance away in your grid. Okay? So how you construct this second derivative is by looking to the left and to the right and comparing it to the one in the middle. Right? And then a is just the distance between these parts. Similarly, if you want to construct this second derivative with respect to y, you look up, you look down, you take the difference, and you get it out, right? Okay. So these are really calculable. We can just go into the array and go line by line, grab every single element, and ask it to compare the values above and below, the values to the left and the right. Take these two values, add them together. Right? Okay. So here's what it looks like in 2 dimensions. This is to the left, this is to the right, this is to the left, this is up, this is down, and this is the one in the middle. All the terms are just added together because we're assuming that dx and dy are the same length. So they're just, right? So check out what they do. This is really fun. Now we have an equation here. This thing, phi of x and y, that depends on its neighbors. Right? So if I just take this thing, this is supposed to equal 0. If I just multiply the a squared, that disappears, and I move the 4 phi to one side, then I have something that's at the location that's equal to the neighbors. So this isn't a time evolution like we've seen before. This is simply saying that I need to match the contours around me. There is some shape to the function, and I'm going to move the piece where I am until that shape matches. Does that make sense? Okay. So we do that. We go now to the next line here. Come on now. Okay, here it is. Right? So we just say something like phi of xy is equal to its neighbors to the power 1/4. Right? And essentially, if you looked at that, you look at it very carefully, what is that saying? Oh, it's an average, right? That's all we're doing. We're looking around at the objects next to us, and we're averaging. Good. So here's what we can do. We can do that problem. We take that box, okay? On the very top, we hold it at V. On the other edges, they hold them at 0. And then we just keep updating that box, update the box, until it doesn't update it. Right? Because it solves this equation everywhere. Let's try it. Here it is here. You create phi. Remember, that's just an array. You hold the top equal to v. You need another one called phi prime. That is going to be the array which you put the new values in. And you're going to swap back and forth between phi and phi prime. You're going to use phi to update phi prime, and then you switch them, use phi to update phi prime, and so on and so forth. Right? Here we have, here you have the new potential. You have I equals 0 or I equals m, or j equals 0 or j equals m. What is this statement saying? This one, if I equals 0 or I equals m, or j equals 0 or j equals m. Yeah.
Is the box mentioned at the origin?
No. The box is just a box, it's an array. Those are your boundaries, right? So let's look at my box. My box is an array of size m plus 1. If I or j is 0, I'm either at the top or the left side wall. If I or j is m, I'm either at the bottom or the right side wall. Right? So now we say, okay, you're at the boundary, just don't do anything. Just leave the boundary as is. This is a boundary problem. Boundaries stay fixed, everything else changes. Right? Okay. And then, if you're anywhere else, update the value. Okay. You walk through this array. You use this I and j loop. If you want to walk through a 2D array, you need 2 for loops. First, you walk through every value of j. Then you take the next value of I, and you walk through every value of j. Then you take the next value of I, and you walk through every value of j. That's how we walk through the array, right? Line by line. Okay. There's some other stuff here. You see delta greater than target. Target is the target accuracy. What that means is that we are going to look for the differences between phi and phi prime. You're going to see that in the next page. You're going to take the difference between them, and you're going to look. Once the difference between them gets below this target accuracy, you want the simulation to stop. And in fact, that's exactly what happens. Here, you calculate delta, which is the maximum value of the difference between phi and phi prime, which is the new and the old arrays that you just calculated. So you'll need to hold on to both arrays, right? You update into one, you subtract from it to see how much it changed, right? And then you swap them. And it keeps going until you make this image right here, which is beautiful and has voltage at the top, 0 at the walls, and this cool little curve of voltage throughout the interior, right? Okay. Does this process make sense? We can do this for something with potential in it. Notice here we have the same expression, but now we have charge on the right-hand side. That's okay. This is a function of x and y, right? And what we can do is we can, again, try to isolate phi here. And that will just be equal to the average of everything around plus any charge where I am. Right? And that is all you do to add charge. It's one little line. Okay? We're going to get into faster methods. We're going to talk about over-relaxation, etc., the Gauss-Seidel method. But I think the easiest way to do this is to just start by doing it. For this particular problem, what did we have today? Oh, no. Oh, no. I think we're going to do 9.1. I think I put the dates wrong there. Let's have a look. Yes. Okay. So we're going to write a program, or you can start by modifying example 9.1. I would recommend while you're working on this with a colleague, try to think about how you would do example 9.1. You just saw me sort of walk you through it, right? So now kind of put that aside. Don't have the book open for that. You can have it open for the stuff that's right before it. But see if you can recreate example 9.1 with your friend, and then compare it to the code that we just wrote. Does that make sense? Okay. All right, let's break up into groups then. If you haven't worked with someone before.